basically, hold on. Let's all set up here. Okay, can you hear me? Where's my little pencil? Okay, so we're going to work through problem 3.3b. Again, just to reinforce it. And I'll try to draw it on here if I can figure out how we can make it work. Nope. Quite what to do here.
You see how on the top it has the red pencil and then the paper?
Yeah.
You gotta make it have that little hand. I don't know what you did last time. There it went. There it goes.
Yay. Okay.
Once that little hand's on there, we can
You can see it.
draw
Okay. So what you need to do is break it into the different forces. So like we had before, we have the square, and you got the W down. You got your wall, or whatever it is. You got an unknown force P, and then you know that your mu equals 0.35. Is that right? And what they want you to do is find the force P. Make sure I got that right. 3B. For the block shown, find the value P required to keep the block from slipping if the angle theta is 10 degrees and W is 10 pounds. So our givens are that theta equals 10 degrees and W equals 10 pounds. So the first thing you want to do is break it into vertical and horizontal components, which we did. So you're going to have, there's your horizontal plane, and you know that, and that's theta. So you know that is P vertical. That doesn't look very good. P V, and then that force is going to be P horizontal. Then from your laws of trigonometry, you know that the sine of theta, which is that, equals, sorry, I can't write very clear on here. Sine of theta equals P vertical over P, or sine is so opposite over hypotenuse, right? And then you also know that the cosine of theta equals the P horizontal or adjacent over the hypotenuse. So you know those things. And from those you can also derive that, sorry, I lost my train of thought. P vertical equals P times the sine of theta, and P horizontal equals P times the cosine of theta, if you rearrange those equations. So I'm going to erase that so I can just write that so I don't run out of room. Because we're building a formula here that's going to help us with this problem and the next one. So you've got the PV equals P that figured out. Step 2, you realize that the P force creates a normal force from the wall that pushes back on the block at a magnitude equal to pH. So there's going to be a force equal to pH, which can either be called Fn or normal. I think our book calls it normal, so we'll call it normal. And you know that that equals pH, right? Everybody following that? Okay. So the magnitude of the normal force is also equal to P cosine theta. So this, that also equals that, right? Because except they're opposite in direction. Okay, so to complete the force diagram, notice that the total downward force will be equal to, so everything going down will equal, what's that over there? Everything going down will be equal to the total of W plus the P vertical, or W plus P cosine theta. So all of the downward force equals downward forces equal W plus P sine P times the sine of theta. Then the total upward force on the block will be equal to the frictional force, which is equal to the normal forces times the coefficient of friction, or N times 0.35, right? So from step 2, we know that the normal force equals P cosine theta, so the frictional force equals P cosine theta times 0.35. So the upward forces equal P, from our deductions, equals P cosine theta times the mu times mu, or 0.35. So then all you have to do, all that's left to realize for the block not to slide down the wall, is that the frictional force must be equal to the W plus PV, or frictional force equals W plus PV. And if we substitute the values from the previous step, we get, I'm running out of room. So W plus PV, that's what we're working with there. W plus PV, so the frictional force must be equal to that. That's F prime, equals that. So we substitute the values from the previous step, and you get P cosine theta times 0.35, which comes from the upward forces. Let's get that. So P cosine theta 0.35, P times the cosine of theta times 0.35 equals W plus P times the sine of theta. Okay. So since we know that W equals 10 pounds and theta equals 10 degrees, you plug in these figures, you got the cosine of 10 degrees is 0.985 right here, so I'm going to put that right there. simplifying that, and these are times 0.35. Simplifying that, you get P, I did my math right, you got P times 0.345 equals 10, because W equals 10 pounds, plus P times 0.174. And then you switch to your algebra, and that's where you have a problem with it, right? So technically, what I was thinking was that you subtract 0.174 P from both sides, then you would have 0.171 P. Is that right? I'm running out of space.
On the right hand side, you can scroll down.
You can?
Right there, you
Oh,
see it?
that's cool. Awesome. Okay. So if you subtract that from both sides, then you would get P times 0.171 equals 10. Then you got to divide 10 by 171 to get P. So why don't you agree with that?
How did you subtract 0.174 without subtracting P? If you're multiplying P on both sides, right? So when you subtract, you have to subtract both of them. So initially it would be P.
Well, we don't know what P is.
I know, but when you do the math right,
Yeah.
you have P times 0.345 minus P times 0.174. So when you combine like terms, you would have P 2P. Or not even, you would have P minus P, so that's 0.
Well, if you do it in simpler terms, like
yeah, they cancel out. When you do that,
yeah.
they cancel out.
Can you write it on here? Or you don't want to? That's fine.
I don't. You have P
Yeah.
times 0.345, right?
Yes.
Is equal to 10 plus P times 0.174, right?
Yes.
Now, if you're gonna swap stuff, you would have to divide this one to take this out from there. And the way you're doing it is you're subtracting. So you would go subtract P times 0.174 is equal to 10, right? So when you subtract, that cancels out because P minus P is nothing. And then this ends up being 0.171. You understand what I'm saying?
Yeah. But
yeah,
what?
you're trying to solve for P, so that math doesn't, the way you did it doesn't
But it
work.
came up pretty close.
Yeah, well, I did it a different way and I came out close, but that's not the right answer.
The theory I was going on was like if you have 5x equals 3x plus 2.
The way I did it was you have P and then you have your, I did this as x. And then you have your, right?
Yeah.
I need to figure, I haven't done the math to figure out what that force is, that force that's going this way, because this is equal to this.
Right.
And then when you, because this is 10 degrees, and this is P, so if you just figure out what this force is, F1, you can do P is equal to, because it would be sine of 10 degrees is equal to PV over P, right? and PV is F1. So if you do, it would be P is equal to um, um, PV times sine of 10 degrees. What I did was I made this 10 pounds because that's what your W is. 10 pounds plus the 0.35, and I came out to 59 point something. So I was wrong there. I did it without the 0.35, and I came out to 57 something. So I think where I'm wrong is on my force, my downward force, the one that you were saying. I think that's where I'm messing up. I need to figure out my downward force. Because you have, your downward force is W plus P times sine of 10. So we go 10 plus P sine of 10 is equal to 0. Negative 10, that cancels that out, and divide by sine of 10. I don't know, that'll work. But do you have a trig calculator?
Want the one on the screen? That's the one I have.
Oh, I have mine.
Okay.
Kind of a pain trying to figure out this stuff.
It is. I hate it.
Okay. I came out with 57.58. And that's off by a little bit still.
58.45. Well, the algebra problem. I mean, if you have like a simple problem, 5x equals 3x plus 2. So 5x minus 3x equals
2x
2x
is equal to 2.
equal to 2. So
And
then,
you divide by 2 and x equals 1.
right. So why didn't,
Because when you're bringing your P,
the p is the x, right?
yeah, but you're not. I don't know, I just feel it's not right. I don't know why, I just don't think it's.
I don't think
To
we
me,
need
it doesn't look right.
I don't think we need to spend all year on it. This is like, I mean, the next chapter is so easy compared to this. Or the next section, I don't know. I mean, but it's not exact, but I think it's just in the rounding up. And that's where I got that.
Yeah, because the actual number up there is 0.344
Yeah,
something something something.
yeah, it goes on forever. But if you,
Okay, let me do it without rounding and see what happens.
okay,
Dylan?
The answer in the back is 58.45.
Still not like, it's like a hair,
That's a
which is
round
not gonna make a difference, I don't think.
So I think we can move on.
Yeah,
Now, if you want to, the way from this information or this formula that we derived, you can move on to 3.3C, and you can use the same formula where that was. F equals W plus PV. Where did I get that? Let me see. The question for 3, see if I wrote that down. The question for C was, for the block shown in figure 3.7A, find the weight for the block that will result in slipping if theta equals 15 degrees and P equals 10 degrees. So we're changing our variable. Oops. Now we're doing 3.3C. And what is theta?
15 degrees.
15, and what was the other thing?
Your P is 10 pounds.
P is 10 pounds. And it wants to know what? I don't have it. What's the slippage?
Find the weight of the block, so we need to find W.
We need to find W. And from before, we derived the formula by going through all of this, that F equals W, or force friction, which is F equals W plus PV. So if we use that same formula, F prime equals W plus that. Substitute your variables. You know that we want to know what W is, so you can switch that around and you can say W equals F minus PV, right? Or F friction minus PV. So then you know what your W is. And you know that the friction force is equal to the mu times the P times the cosine of theta from what we got above. Right? Following me? So that equals 0.35 times the P. This is all under F. P, which is now 10, or was 10, times the cosine of theta, which is the cosine of 15, is 0.966. And then all of that minus P, which is 10, times the sine of theta, because that's PV, which we got way up here. PV equals P sine theta. So P sine theta, and sine theta is 0.256 sine of 15. So then if you do all that math, the way what I got was 3.381 minus 2. I don't know if I did this right. Let me check that.
Yeah.
Is that right?
Yeah.
Huh?
Yeah.
Equals 0.821.
Oh, I used the actual without rounding, and I got the answer in the back.
Okay, good. What was the actual without rounding?
The actual answer without rounding?
Uh-huh.
0.792549941.
part of your assignment was to do those. Did anybody try, or did you just copy?
I'll try. I didn't get them.
Do you understand it better now? Or is it still a mystery? I think the book, I mean, I don't know if we'll really, engineers use this, of course, but I don't think we need to spend an inordinate amount of time on it. We've already wasted 2 days. But, do you feel like you understand it better with this explanation of breaking it down into a problem? Okay. Okay, what I want to do now in our last 30 minutes today then is start talking about moments, which I think is much simpler. So, does this just go down and down forever, or does it ever stop? Okay. So a moment, which is section 3.4 in the book, is kind of like a motion, like a wrench. I don't know if you read ahead, but like when you're trying to undo a bolt or something, that's a moment force, a rotating force. And things rotate all the time, and you have to keep them in equilibrium. Your building has moment forces in it, and you have to keep those static, I guess, still. So the moment is a tendency of a force to cause rotation about a given point or axis. So if you have a beam or a column or something, and you have something hanging off of it, cantilevered, this is your support point, and you put a weight here, this is going to tend to rotate unless you make this stiff enough, if this is strong enough to hold it out. That's a moment force. And the distance here is called the lever arm, or the moment arm. And a moment force is always equal to the magnitude of the force times the moment arm. So if you have 10 pounds or 10 whatevers, and this is, 10 feet from there, it's going to be 10 times 10 is going to be 100 foot-pounds if you're measuring in feet, or inch-pounds if you're measuring in inches. So and if you're going counterclockwise, it's going to be a negative moment. So this is going to be negative. If it's going to rotate, if it was over here on this side, or if something was pushing this up, I'm sorry. If something was pushing on this side down, if there was more force on this side, it would go this way. So that would be a positive moment. That makes sense? We're going to do a lot of this problems in this, so you do need to understand this. So if you want to, the example they give in the book, if you want to increase your moment, your strength, like if you're trying to undo a tight bolt with your wrench, and you got a little bitty wrench, you're going to have to use more force, because there's your bolt, and your wrench is your moment arm. If it's only 3 inches long, you're going to need a lot of force to get that loose. But if your wrench is longer, if you put a pipe on it, like it says in the book, make it 10 inches, you'll have a lot more force to get that loose. So, because the moment force equals the magnitude of the force times the moment arm, so that increases. Everybody understand that? Okay. So then if you want to increase, so then it gets into 3.6 was where I'm at. Talking about mechanical couples. And that's where the mechanical couple acting on a body causes motion of rotation rather than motion of translation. A mechanical couple can be held in equilibrium only by the addition of another mechanical couple. It cannot be balanced by a single force. A person's two hands operating a steering wheel constitute an example of a mechanical couple. So it has to have a balancing force. A moment couple is the product of the forces and the perpendicular distance between their lines of action. So you have to have two different forces to balance, to keep that still, and they have to be equal to make a mechanical couple. So, and that's, and it shows that in this wheel problem, and I'll show you that, how they did that here in AutoCAD. Let's see. Bring this over here. Why is all that there? And you can figure out these problems because you're going to have homework on this as well. Doing AutoCAD, this is not necessarily math. It's more of the forces like we talked about earlier. So you have this a 12-inch diameter wheel that weighs 400 pounds. This is my wheel, it's drawn to scale, weighs 400 pounds. Determine the magnitude of the horizontal force shown in figure 311A required to start the wheel over the 3-inch high block. So then you want to make that into a force polygon like we did last week, I guess. I've drawn this green line from there. The green line you can see is 4 inches long. It's going down and it starts at the 9 inches above the ground, which is this part. I measured all that out earlier. Then you're going to draw a line where this block that it has to go over goes up and intersects that point 9 inches above the ground, and then your force is going to be this right here, where the end of the 400 pounds over to where that intersects, and that is, oops, the length is 3.7 of an inch. I had this in architectural units, not decimal units, but the force is going to be, 300, whatever that 7/16. It says 330 in the book. So that's how you would figure that problem out. And there is a problem you're going to do for homework. You're going to do problems 3.7a and 3.7b, which, if you just follow these examples, are just exactly like that. 3.7, the other example is figure 3.12a represents a masonry pier that weighs 10,000 pounds. Determine the magnitude of the horizontal force applied at the upper left edge, and it will be required to overturn that pier. So you can follow that solution and do problem 3.7b as well. Do you think y'all understand that, or do I need to work through that example problem? Okay. I think this is pretty simple compared to friction. So, and I'll put this, I haven't put it on the Canvas yet, but you'll do 3.7a and b, showing me your work. I want the papers turned in for homework, and I need to check your, if you haven't done it, you need to do 3.3a, b, and c, and show me your work too. Just, I think working through it will help you understand it. But if we're moving on, we're going to move on a little bit further in the book, because I think this is really pretty simple. You just have to read it and understand it. Moment forces on a beam is section 3.8 in the book. Turn this over. architectural problem, or, a design issue, you have to understand these forces. Um, if you have a beam sticking out of a wall, or some sort of construction, you have a concentrated load there that is, that may be 4 feet, as according to the book, or if you move it out 2 more feet, and even out to the end, another 2 feet. So what is going to happen to that load? Is it going to be, say if this is 100 pounds right there, what's going to be the moment? What is that going to equal? Anybody know?
400.
That's right. So that right there is going to be 400. And then as you go out further, you moved it out, what would it be? 600. And then of course 800. And are these positive or negative? Right, because they're clockwise. So you can see how the force is greater the further you get out. Now at the same time, you can have a uniformly distributed load, and that's shown in the book by, or in structural problems, usually by something like that. And they'll give you an amount, as they did in the book, which is 200 pounds per foot. Right? Yeah. So to figure that out, you can, since it's uniformly distributed, you can take, and it tells you that that's 6 feet long. You can take that, and you'll know that at 3 feet from in the middle of it, which will be at 3 feet, you're going to have a concentrated load that would be 200 times 6, which is 1200, right? So that's how you can figure that out on uniformly distributed loads, which is what we're studying now. And so then this is 4 feet, and then that's 3 feet, that's going to be at 7 feet. It's going to be your arm, or your moment arm. So this load will go like that. What will that be? Someone multiply that. 8,400. And that is positive. That makes sense? Uniformly distributed loads. When you're figuring moments too, you always need to know the point of rotation. And in the book it calls that A. That's where that's gonna be the center of your rotation. And when you're figuring these problems out, you always have to work from the same center. You can't move your center around. So this leads into equations of moments, which is what we're going to go into. And to keep something static or in equilibrium, you have to, all these things have to come up to 0 in the end. So there's 3 fundamental laws of equilibrium. One is the algebraic sum of the horizontal forces equals 0. So sum is like that, of all the horizontal forces equals 0. The algebraic sum of all the vertical forces equals 0. Oops. Sum of the vertical forces equals 0. And the sum of the moments of all the forces about any point must equal 0 for it to be in equilibrium. So the sum of the moments equals 0. All those things must be true for it to be still in equilibrium. So they show you is a coplanar, it's, in equilibrium. But you also have, you can have a beam that has, a support here and another support at the end, and it can have loads, you know, in two different places on the top. Well, to keep the math simple, you know, this could be 200, this could be 800 kips or pounds or whatever going up, and this could be 500 and 500. Of course, that all, the sum of the downward forces equals the sum of the upward forces. That all equals 0, so that's in equilibrium. So you just, that's how they figure out the strengths of materials, is by making sure everything is in equilibrium. That's very simple. At the same time, you also need to figure out, your moments need to equal 0. The third law of the equilibrium. And for this they show a beam of some sort. They have a support there, and a support at the end. They have a force coming down there, and a force coming down there. And then they show the moments that are going to happen with these forces. That'll tend to go that way. That's an example C. And here's your center, point A. So if you want to create an equation of moments that will end up being 0. So if you take the point A, marked A on the line of action at the right support, and write an equation of moments. Consider moments that tend to cause a clockwise rotation as positive, and the ones that cause a counterclockwise rotation as negative. So you want to do your positive. Clockwise would be that one, right? We're using the same amounts as shown in that figure 3.15, so that's going to be 4,400 or 4.4K, and your distance is around point A, that's 6, and so that's going to be 20 feet. So in your problem you have 4,400 times 20 is going to be this moment right here. And then your other ones are going to go the other way. So you'll have minus, you've got 4,000 times 14. And then you've got an 8,000 times 4, because it's 4 feet from there according to the book. So that should come up to equal 0. And so then you would know that it's going to be in equilibrium. Does that make sense? Are we meeting in this room or the next room?
Next room.
Okay, why are you in here?
Chilling.
Okay.
What time is your class over?
Technically not till 11:50, I mean 12:50, but we're going to try to get done a little early. Is anybody in there yet?
No, no one's in here yet.
Okay. So does that make sense? Any questions on that? Huh? I wanted you to also do, number 3.9A. And then it gets into reactions. Do you want me to try to go over that real quick, or? Okay, so then to be clear, and I'll write it on the canvas, has anybody worked out those 3.3A, B, and C? Okay, well then,
That's what we did in here.
Hmm?
That's what we did in here.
okay, for Tuesday's online class, I want you to submit to me, the homework, 3.3A, B, and C, 3.7A and B, and then problem 3.9. I want to see that worked out. And then, we'll discuss the rest of chapter 3. I'll put some discussion points up there, okay? I don't know if y'all are lost. You're not saying anything. For the homework? I want to see worked out, even though we've already done it in class, but I want to see it worked out on your paper. 3.3A, B, and C, 3.7A and B, and 3.9. Okay? And those will be due Tuesday. You need to submit them to me by Tuesday, and then, or give them to me Tuesday morning in here. And then we'll discuss the rest of chapter 3 in our online discussion.